Welcome, friends. Welcome to this academic program. We are discussing Power System 1. In the last few lectures, we have discussed the inductance calculation of the transmission line, where we have seen that GMD GMR method is quite useful to calculate inductance of the transmission line irrespective of its geometry, irrespective of the tower configuration, irrespective of the conductor nature, whether it is a bundle conductor or it is a stranded conductor. GMD GMR method is effectively used to calculate inductance of the transmission line. Moreover, you do not have to write or you do not have to derive any derivation for individual or for separate tower configurations. So with the continuation, today we shall discuss the another important parameter, which is capacitance. Capacitance of the transmission line. So what is capacitance? So you know, when a capacitance is formed, it is formed when two metal plates are separated by a distance, and this gap should be filled with a dielectric. Now transmission line is a perfect example of capacitor. So if this is the conductor and if this is the ground, so in between a capacitance must be formed, because in between air is there and air is acting as a dielectric. And of course, it constitutes the shunt conductance. Y is equal to G plus JB. Although the G is neglected due to its very low value, however, this B will be represented as a whole due to the presence of shunt capacitance. Now, how do you define a capacitance? Capacitance is defined by charge content Q divided by potential difference across the plates. So it is the unit of farad. Now, or how do you derive the capacitance formula? We shall use the similar sort of derivation. Let us derive that first. Let us we have a solid conductor like this. We have a solid conductor like this with radius x, and we have charge storage capacity. Q, and Q is located on the surface of the conductor. Charge is stored on the surface of the conductor like this. So in this case, what will be our first derivation? That is, we can write electric flux density. We will write electric flux density dx. We can write electric flux density dx. So we write dx is equal to, what is dx? Dx is equal to charge per unit area. Now what is area? It is 2 pi x into 1. Why 1? We only consider the cross-sectional view. That is why h becomes 1. So due to that reason, we can write dx is equal to q by 2 pi x. So once we have got the electric flux density, then we can write that electric field intensity. Electric field intensity, electric field intensity Ex. What is electric field intensity? You know, D is related with dx, that is related with epsilon Ex. What is epsilon? Epsilon is called epsilon naught, epsilon r. It's called permittivity of the medium. Permittivity of the medium. Now we have epsilon naught, it's called absolute permittivity. Absolute permittivity, which is equal to 8.854 into 10 to the power minus 12 farad per meter. Or in other words, it can be also written as 10 to the power minus 9 by 36 pi farad per meter. This is what we have as epsilon naught, which is absolute permittivity. Now what is our relative permittivity? What is our relative permittivity? Relative permittivity is equal to 1 for air. Okay, so this expression turns out to be Ex, that is the electric field intensity at x, that will be equal to dx by epsilon naught. We can take epsilon r is equal to 1. So dx, which is equal to q by 2 pi epsilon 0 into x. So this is the expression for electric field intensity at x. So now once we have done that, then we can proceed further. What will be now the potential difference? What will be my potential difference? What will be my potential difference? We assume two surfaces like that. We assume two surfaces like this. One is located at a distance d1 and another one is located at a distance of d2. This is surface number 1, this is surface number 2. And one charge has been brought from surface number 2 to surface number 1. Sorry. So my potential difference V12, my potential difference V12 can be written as my potential difference V12. So you have to integrate Ex into dx with a negative sign from 2 to 1. So if you evaluate this, your expression would be V12 is equal to, so you can change the term 1 to 2, Ex becomes q by 2 pi epsilon 0 into dx by x. So this becomes V12, that will becoming, so if you integrate, you see q by 2 pi epsilon 0, it's constant. Then ln x will be your integration. Now if you put the limit to surface number 2 as d2 and surface number 1 as d1, then this expression becomes q by 2 pi epsilon 0 ln d2 by d1. So as a result we can write capacitance. As a result we can write capacitance C equal to Q by V, which is equal to 2 pi epsilon 0 by ln d2 by d1. Now we can use an approximation. You see d2 and this d1 are the any two surfaces outside of the conductor. So just like we have done in case of inductor, we can approximate d1 as conductor radius r, and we can approximate d2 as a capital D, where D is the distance from one conductor to another conductor. So what we have got? We got C is equal to 2 pi. Now you should write the epsilon 0, it is 10 to the power minus 9 by 36 pi over ln d by r. So altogether it will be 10 to the power minus 9 by 18 ln d by r, and unit should be of course farad per meter, as we have considered the per unit length, that is the cross sectional view of the conductor. So this is the capacitance formula. This is the capacitance formula we have with us. This is the capacitance formula we have with us. C is equal to 10 to the power minus 9 by 8 by 18 ln d by r. Now just like the previous case, this D and R is not existed for the real case, because in reality we use stranded conductor. So there are existing lots of n number of conductors. So similarly this formula can be modified as C is equal to 10 to the power minus 9 by 18 ln dm by ds, just like we have done in case of inductance. So here also the same applies in case of a capacitance formula also. D is replaced by dm, which is gmd. D is replaced by dm, which is called gmd, and r is replaced by ds, which is called gmr, or self distance. So this is the formula of capacitance we have derived. Now you must remember this fact: in capacitance calculation you must consider R. You should not consider R dash. In case of inductance you always consider R dash, but in capacitance you must consider R. What is the reason? Because if you see any conductor, now is a capacitor is a charge storing device. Now where charge is being stored? On the surface. Where is being charge stored? The answer is on the surface of the conductor. So if you want to investigate on the of this conductor, you will always find the charge are always storing on the conductor surface. That is why in case of a capacitance calculation we always consider conductor radius as R. However, in case of an inductance calculation, there is a current flowing I. Now this I will set up one magnetic flux which has two parts. One is internal, another one is external. This internal as well as external flux are linking with this current, so that is when an effective resistance is found out, which is equal to 0.7788. So this is the fundamental difference between capacitance and inductance calculation of the transmission line, you should remember. And one more important point, that sometimes earth comes into play while calculating C. However, sometimes it is neglected because the ground clearance is very, very large as compared to the distance between two conductors. So in most of the cases we neglect the effect of earth while calculating the capacitance. Now we have solved these problems already. We have solved this problem already in case of an inductance calculation. Now for the same problem we will solve the same in case of a capacitance calculation. The conductor diameter is 2 centimeters, so radius is 1 centimeter. So we will solve. Now as you know, we have to find out first dm, then we have to find out ds. Now in order to find out dm, we have already evaluated dm as 5.7 meter. We have evaluated dm as 5.7 meter. As far as the capacitance is concerned, this is exactly same as that of an inductance calculation. So it is the repeat work. So I am not doing that. dm was found to be 5.7 meter. However, ds will be little different. Why? Because in capacitance calculation you should always consider the conductor radius. So in order to do that, let us first calculate the self distance of phase A, then we will calculate self distance of phase B, then we will calculate self distance of phase C. These three we will calculate. Now as far as the phase A is concerned, as far as this phase A is concerned, let me figure out how many possible distances are there. So for A phase, we have A1, which is nothing but the radius of the conductor, and we have A1, A2, which is this distance, A1, A2 is this distance. Now how you will calculate? You should drop a perpendicular like this, and then you draw this line. So this is the right angle triangle. So this is 7 meter and this is 6 meter. So A1, A2, it is already done in the previous lecture. It is 6 square plus 7 square. So which is equal to, I think it is 9.22 meter. 0.22 meter. So we have got, so we can write, we have two distances. So we should take the square root. What is the square root? First you can take 9.22 into 0.01. So if you evaluate this, it will come out to be 0.304 meter. 0.304 meter. Right? This is the result for DSA. And I think you can understand this fact that, you see, this will repeat. This will be repeating for C1, C2. This will be repeating for C1, C2 as well. For C1, C2, this will be repeating. So for C phase, we have C1, C2, which is 9.22 meter, and we have another thing, C1, which is equal to R. I think I have done a mistake. It should be A1. So DSC, this should also be square root of 9.22 into 0.01, which is found to be 0.304 meter. Now what we have left with? We have left with DSB. We have left with DSB. We have left with DSB. Now for B phase, what we have first of all, we have B1 B2 or B1 B1, which is equal to R, and we have B1 B2, that is equal to this B1 B2 is this distance. B1 B2 is this distance, which is equal to 8, So DSB is nothing but square root 8 into 0.01, that will be evaluated as 0.28 meter. 0.28 meter. So once we have done all these three, then we should calculate what will be equivalent self distance. What is equivalent self distance? So we have three terms, then so we should take cube root. So we have got 0.304 twice. 0.304 twice. This is 1, this is 2. So we should take 0.304 whole square, and lastly we have got 0.28. So if you evaluate this, on evaluating it will be coming out to be 0.296 meter. You can always verify these data at your home if I have done some mistake on calculating. So now we can calculate the C. So what is the capacitance value? C. So it is equal to, as you know, it is 10 to the power minus 9 by 18 ln dm over ds. So putting those values, 10 to the power minus 9, 18 by 18 ln, what is dm? Dm, I hope it was 5.7 meter. Dm, it is 5.7 meter. 5.7 by, what is ds? ds equivalent is 0.296. So if you evaluate this, it will coming out to be 0.01878 into 10 to the power minus 9 farad per meter. So which is equal to 18.78 nanofarad per kilometer. So for this transmission tower, so if you run this transmission tower for 1 kilometer, it will offer a capacitance of 18.78 nanofarad. 18.78 nanofarad. So one fundamental difference between inductance and capacitance calculation is that while you are calculating inductance, you should always consider R dash, which is equal to 0.7788 into R. And while calculating the capacitance, you should only consider the R. So this is the fundamental difference between inductance and capacitance calculation. Otherwise, as far as the dm is concerned, it is exactly the same. It is the repeat work. While calculating the self distance ds, you should consider R dash for inductance and R for capacitance. This is the only difference. Rest you can do as per your convenience. So with this, I am ending this lecture here. In next lecture, we will discuss some more important aspects on transmission lines. So we are ending here. Next class, we will conclude this module. Okay, thank you.